At the heart of a lot of those old school analog meters, there's this really beautiful piece of engineering, the permanent magnet moving coil, or PMMC. It's an absolute marvel of sensitivity. It can detect the tiniest little whispers of electrical current. But that incredible sensitivity, it's also its greatest weakness. And this creates a huge engineering problem for us. You see, a typical PMMC meter might give you a full-scale reading with just 1 single milliamp of current. So what on earth happens when we need to measure the real world?
I mean, just picture it. On one side, you've got this incredibly fragile, delicate little instrument, and on the other, you have the massive power of, say, a 10-amp industrial motor or a 240-volt grid. If you just go ahead and connect that meter directly to that load, poof, it will instantly overheat, vaporize, and just destroy itself.
So that's the puzzle, right? How do we take a sensor that can only handle 1,000th of an amp and somehow use it to accurately measure a current that's 10,000 times stronger?
And here is the key insight, the real engineering magic. The solution isn't to try and build a bigger, tougher meter. No, the genius is in modifying the circuit around the meter, using some really simple components and some brilliant physics to protect our little sensor and scale its measurement. So here's our game plan. First, we're going to tackle the current problem by building an ammeter and digging into the math. Then, we'll do the exact same thing for voltage with the voltmeter. And finally, we'll pull it all together to see the big picture, the core engineering insight behind it all.
Okay, first up, measuring current. To turn our fragile meter into a tough, usable ammeter, we've got to give the vast majority of that current a different path to follow. We need to create a bypass. Think of it like this. The total current is a massive, raging river, okay? And our delicate little meter is a small, wooden water wheel. If you stick that wheel right in the middle of the river, it's just going to shatter into a million pieces. But what if you dig a huge bypass canal right next to it? Well, then 99.9% of the water flows safely down the canal. Only a tiny, predictable trickle is left to turn the wheel. And by measuring its slow, steady spin, we can calculate the flow of the entire river.
Well, that bypass canal on our circuit has a name. It's called a shunt resistor. It's a precision resistor with a very, very low value. And this is key. It's connected in parallel with the meter. This gives the current a super easy path to follow, making sure most of it bypasses our delicate instrument. Now, of course, that intuitive analogy isn't just a nice story. It is backed up by some fundamental circuit laws. So let's jump into the math and see how we can calculate the exact resistance value we need for our shunt. To figure this out, we need a few key variables: the total current we want to measure, the meter's maximum current and its internal resistance, and of course, the current that's going to go through our shunt. Don't worry, the derivation is a really straightforward 4-step process using the basic laws of circuit theory you already know. Okay, step 1. Because the meter and the shunt are in parallel, Kirchhoff's voltage law tells us their voltage drops have to be exactly the same. Step 2, we just apply Ohm's law, V equals I times R, to both sides of that equation. Step 3, we use Kirchhoff's current law. It tells us that the current through the shunt is simply the total current minus whatever little bit goes through the meter. And finally, step 4, we just substitute that expression for the shunt current back into our equation and solve for the shunt resistance R sub S. And there it is. With this one elegant formula, we can calculate the precise, tiny resistance needed to turn our delicate 1 milliamp sensor into a robust 10-amp ammeter. It's simple, and it is incredibly powerful. Okay, so we've conquered current. But what about voltage? Well, measuring voltage requires a completely opposite strategy. Instead of bypassing energy, we actually need to absorb it. Let's use another analogy, shall we? This time, think of voltage as super high water pressure in a pipe, and our meter is a really sensitive pressure gauge. If you connect it directly to that pipe, bam, it explodes. So what's the solution? We stuff a dense, restrictive sponge inside the pipe just before the gauge. That sponge absorbs almost all the pressure, so our sensitive little gauge only has to measure a tiny, safe fraction of the original total. In our circuit, this sponge is called a multiplier resistor. And I want you to notice, it's the exact opposite of the shunt. It has a very high resistance, and it's connected in series with the meter to drop most of the voltage before it can ever reach the delicate coil. And hey, just like before, we can prove this whole concept and find the exact resistor value we need using those same fundamental circuit laws. It's another really elegant derivation. So So we'll define our variables, the total voltage we want to measure, and the meter's known current and resistance. And again, it's a simple four-step process, but this time we're using the rules for series circuits.
So remember, in a series circuit, the voltages add up. That means the total voltage is the sum of the voltage drop across the meter and the drop across our new multiplier resistor. Then we apply Ohm's law. Now, because the current is the same everywhere in a series circuit, we can factor it out. And finally, we just do a little algebra to rearrange the equation and solve for our multiplier resistance, Rs. And boom, there it is. The formula to calculate the exact high-value resistor we need to safely measure massive voltages. With this, we've successfully designed both a practical ammeter and a voltmeter. Pretty cool, right? So let's just take a step back and really look at what we've accomplished here. We started with this incredibly fragile sensor, and using nothing but some resistors and basic physics, we've transformed it into two powerful real-world measurement tools. This matrix here really sums up the two totally distinct strategies. To make an ammeter, we connect a very low-resistance shunt in parallel to bypass the current. To make a voltmeter, we connect a very high-resistance multiplier in series to absorb the voltage. Two different problems, two completely opposite solutions. Now, this leads to a supercritical real-world design consideration called the loading effect. See, because our meters aren't perfect, they can actually slightly alter the very circuit they're trying to measure. Ideally, an ammeter should have zero resistance, so it doesn't block any current at all. And an ideal voltmeter, it should have infinite resistance, so it doesn't draw any current away. Getting as close to these ideals as possible is a huge goal for any instrument designer. And this, really, this gets to the heart of everything. We started with a simple mechanical device that could just detect a tiny magnetic force. But by pairing it with rigorous mathematics and a genuinely clever design, we've adapted it to measure the invisible, massive forces that power our entire world. That is the essence of electrical engineering. So I'm going to leave you with this question. What other fragile sensors exist out there in your world? Maybe it's a microphone, maybe a temperature probe, maybe even something like the human eye. How could they be transformed into powerful new tools with the right kind of circuit, a clever analogy, and just a little bit of math?